This is the next question we are going to discuss. If you are about to start watching this video, my advice would be you have the question now, take a screenshot and try the question first and find the answers, and then watch the explanation so that you can see where you have done correctly and the areas where you could do better. Okay, that way it will be quite useful to you. So let's get on to the question. So what does the question say? A car started moving at an acceleration of simple a from the bottom of a cliff along a horizontal road. A bomb was fired from an artillery from the edge of the 160-meter tall cliff at an initial velocity of u while creating an angle of theta with the vertical. Okay. 2 seconds after the car started its motion. Right. So car starts moving, and when the stopwatch, no, you press the stopwatch as car starts moving. When the time on the stopwatch is 2 seconds, bomb is fired and the bomb is landing on the ground. And the height of the cliff is given as 160 meters, and the maximum height reached by the bomb is 180 meters from the ground. And the horizontal distance from the bottom of the cliff to the place where the bomb lands on the ground was found to be 160 root 3 meters. Ignore air resistance and take root 3 as 1.7. So these are the information they have given us. Let's try to plot a diagram before we start finding the answers. So the diagram, it's going to look like this. Let's draw the cliff. This is our cliff, and at the bottom of the cliff, here we have a flat road like this leading. Fine, and then from the bottom of the cliff, there is a car which starts its motion with an acceleration. Right? So this is a car. Its initial velocity is 0. It is going to move. So time on the stopwatch when the car starts, let's take it as 0, and the car is moving at an acceleration 8. At the meantime, from the top of the cliff, not at the meantime actually, when the time on the stopwatch is 2 seconds, this 2 seconds after car started moving, a bomb is fired at an initial velocity of u while creating an angle with the vertical of theta. So the angle is theta with the vertical, remember, right? So if the angle with the vertical is theta, when there is a velocity like this, we can take components. So the vertical component is u cos theta, whereas the horizontal component is going to be u sine theta. U cos theta, u sine theta. Both initial velocity and angle are not given. We will have to find it, right? And we know when you fire the bomb like that, the trajectory of the projectile path, that's going to be like this. It's eventually going to hit the ground somewhere here. All right, fine. And they have said the object reaches a maximum height of, not the object, actually the bomb reaches a maximum height of 180 meters from the ground. 180 meters from the ground. So if we consider that, it should be like this. 180 meters from the ground, whereas the height of the cliff is given as 160 meters. So let's quickly mark those numbers over 160 meters, and this is 180 meters, the maximum height. What are the other things we can mark here? On this level, the height of the cliff is 160. The maximum height reached from the ground is 180. Therefore, this particular height should be 20 meters. This height, which we will need later. That is 20 meters. And we know at the maximum height, the object will possess only the horizontal velocity component, because the gravity, which is going to be u sine theta, and the vertical component is 0. I hope you are clear with that. When the object goes up, the vertical component will keep reducing because we have the acceleration downwards. Downwards acceleration is 10 ms minus 2. But since we are ignoring air resistance, we can't expect any horizontal accelerations. And initial velocity in the upward direction is u cos theta, whereas initial velocity in the horizontal direction is u sine theta. And what are the other things? Okay, let's take the time taken by the, I'll mark certain points. Now, let's take this point as A, maximum height as C, and the point where the bomb lands on the ground, I'll take it as point C for our reference later. Okay, so let me write down something. Time T. What is T? Time taken by the bomb to reach C from A. The total time taken for the bomb to hit the ground. All right, fine. So that's something you need to know. And the other thing, from A to C, this is the total path. I mean, the entire motion of the bomb. From A to C, you can see the object has gone down 160 meter distance. And horizontally, they have told in the question, I forgot to mark that. So what is the horizontal distance the bomb has moved? That is 160 root 3 meters. 160 root 3 meters. 160 root 3 meters. All right, fine. So from A to C, if you consider, there's a vertical displacement component of 160 meters. And the horizontal displacement will be from A to C, 160 root 3 meters. I hope you all understood this. Object started at A, went up and goes down. Actually, this should be taken as B. Sorry, I'll take it as B. Yeah? I have marked both as C. So let's take it as B. Let's take it as C. A to C. From A to C. When you say displacement, from starting level to finishing level. So vertically, it has moved 160 meters. This part is important. Horizontal, okay, fine. Now, first question: find the time taken by the bomb to land on the ground, initial velocity, and angle theta. So there are three unknowns we have to find. T, we have to find U, you have to find T. Sorry, theta. Three unknowns. So we will need three equations. Okay, right. So 20 meters here height. So by looking at the equations, from I think we should start from A to B rather than going from A to C, because when you go from A to C, there are quite a lot of unknowns. So it's better if we start from A to B. So I'll start the working from there, from A to B, starting from A to B. Right. What are the information we know from A to B? Vertical displacement is 20 meters, and the vertical final velocity is 0, and the vertical initial velocity is u cos theta, and the acceleration is 10 ms minus 2 downwards. So displacement, velocity, initial velocity, acceleration, when you consider these things from A to B, let's apply the equation v squared equals u squared plus 2as in the upward direction vector. So direction must be defined. So final upward velocity is 0. Initial velocity in the upward direction is u cos theta squared plus 2 into, now for A in the vertical direction it is downwards 10, but I'm applying the equation in the upward direction, therefore I should substitute minus 10 into, from A to B, the vertical displacement is 20 meters. Vertically it has moved 20 meters. Okay, so here it is 20 into 20. 2 into 10 is 20, 20, 20, 20 squared, but there is a minus, so that minus goes to the other side. It becomes 20 squared equals u cos theta squared. From that, I can say u cos theta is equal to 20. So we have derived one equation, right? Fine. So that, let's leave it there. Right. Now let's go from A to C, because we know a lot of information from A to C, the displacement, all those things are known. So let's start there. From A to C, if you consider, I'm going to apply the equation downwards. S equal qt plus half at square. From A to C, now you can apply the equation twice from A to C. One is in the vertical direction, the other one is horizontal direction. bomb has moved vertically as well as horizontally. So you can apply this equation separately twice. Vertical displacement downwards we discussed already, that is 160 equals what is the initial velocity in the downward direction. In fact, the initial velocity is upwards, u cos theta, u cos theta. Therefore, we have to substitute minus u cos theta into t plus half into, in the downward direction acceleration is 10 into t square. Okay, at 160 that is equal to minus, instead of u cos theta I can substitute this 20, so minus 20 t plus 5t square. So what happened, I'll underline something. This is u cos theta equal to 20, that 20 is substituted here. I hope you can understand. Right, and moving on, this is a quadratic equation, and I'll take 5t squared and 20 is okay, then 0 here. Here we have 5t squared minus 20t minus 160. 5 is common, therefore we can divide the whole thing by 5. Then therefore we will be getting 0 equals t squared minus 4t minus 32. If you divide 160 by 5, it's 30. 0 equals minus 32. We have to get minus 40. So you can use 8 and 4 as the factors, O-level quadratic equation. So minus 8t plus 4t minus 32. And if you take t common, t minus 8 plus 4 again t minus 8. So we can take t minus 8 common. Therefore here we'll get t plus 4, that is equal to 0. So time will be 8 seconds, not time will be minus 4 seconds. And we all know minus values for time, it's not appropriate, it's not correct. So you can ignore that and consider 8 seconds. So time is 8 seconds. Just underline that with green, maybe I might need it later. Okay, fine. So I hope you can understand that. Right, so one by one we are solving things, and the next thing we can do is from A to C we can apply the equation horizontal, because the object has moved horizontally as well. So horizontally S equals ut plus half at squared. Horizontal displacement is 160 root 3. Horizontal initial velocity is u sine theta, because the angle is created with the vertical. So horizontal is u sine theta into time. Time we know, that is 8. We have already found. Plus horizontal acceleration is 0. There is no horizontal acceleration because the resistance is ignorant. We have 160 root 3 on the left side. Here we have 8 u sine theta. Therefore, we can divide 160 by 8. It will be 20 root 3 equals u sine theta. This is the second equation. Now we have two equations, don't we? I'll rearrange this so that it will be less confusing for you. I'll write this on the left side, the number on the right side. So u sine theta is equal to 20 root 3. Two equations consisting of u and theta. So if you simplify them, you can get the answer. So I'm going to do something like this. Let's divide 1 by 2. Sorry, let's divide 2 by 1. 2 by 1. Why is that? Because when you divide 2 by 1, you'll be getting u sine theta divided by u cos theta. So u and u will get cancelled off. When you divide sine theta by cos theta, you will be getting tan theta. And on the other side, it is actually 20 root 3 divided by 20. If not, right? So when you do that, sine theta over cos theta equals to 20 root 3 over 20. So this is tan theta on the left side, on the right side, root 3. And we all know root 3 can be written as tan 60. Therefore, we can say theta is equal to 60 degrees. So we have found the time and we have managed to find the angle as well. 60 degrees is the angle, right? And if you substitute that in the first equation, we can substitute that in the first equation. So if I do that, first equation will give me u multiplied by cos theta, that is cos 60 equals 20. And we all know cos 60 is half, equals to 20. Therefore, u is equal to 20 into 2, 40 meters per second. Right? So 3 things were supposed to be found here. Time, 8 seconds, done. Initial velocity u is 40 meters per second, and the angle theta, it is 60 degrees. So we are done with that. 3 unknowns were there, so we should write 3 equations and solve the equations. All right. So with that being said, let's move on to the next one. Okay. Once bomb lands on the ground, the objects within an area of 20-meter radius around the point of impact are subject to severe damage. Find the range of A. Find the range of A, which will put the car under the danger of incurring severe damage. Now you can see the bomb is going to land here. The bomb is going to land here. So instead of this C for a while, this C. Right. If the bomb is landing here, from that point, a 20-meter radius is the danger zone. That means from here, 20 meter, from here, 20 meter. Okay, that region is danger. I mean, I'll highlight. I hope you can understand. This region is the danger zone. Now the area I have marked, this is the danger zone. So we don't want our car there. We don't want our car there. If the car is here, it's safe, or else if the car is here, it's safe. So they're asking the range of the value for acceleration of the car. All right, fine. So what is 160 root 3? They have given us root 3 as 1.7. So that's going to be 116 to 1.7. So that is, in fact, 16 into 17. 16 into 17, that would be 272 meters. 272, because 16 into 16 is 256, and you add another 16, so you get this value, 272 meters. That means if the car has traveled a total, see if you can understand this. The car has traveled a total distance less than 252 meters. Or else, if the car has traveled a total distance of greater than 292 meters, then the car is not in danger. I hope you all understood that. The bomb lands at 272 meters from the bottom of the cliff. And if it lands there for a 20-meter radius, so this is a radius, this is a radius, it's a danger zone. So this side and this side, so to 272, I have added 20, that is 292, and I have subtracted 20, that is 250. So if the car's displacement is less than 252 or greater than 290, car will be safe. So when the bomb lands, the car is here, the car is here, then the car is safe. So I'll write that down here. Okay, so that's the condition. And one more thing, now the time taken by the bomb to hit the ground is 8 seconds. Time taken by the bomb to hit the ground is 8 seconds. We know that. So when the bomb hits the ground, when the bomb hits the ground, car has traveled for how many seconds? For 10 seconds. Because car started 2 seconds before the bomb was fired. Okay, so if bomb takes 8 seconds for its full motion, car was moving during those 8 seconds, and also it was already moving 2 seconds before. So overall, car has moved for a total time of 10 seconds. So I hope that part is clear to you. Okay, so let's continue and finish this off. Okay, I just created some space so that we can do the calculations which are related to the car. Now, talking about the car, you can see it starts from rest. So for car, initial velocity is 0 and its acceleration is a, and it has traveled a time of 10 seconds. All right. Now, displacement minimum, to avoid danger, it should have a displacement less than 252. All right. So we can apply the equation for two situations. When the displacement is 252, you can find the acceleration. When the displacement is 292 meters, we can apply the equation. I hope you guys understood. If it goes slowly or faster, much faster, it's safe. Even if it travels slowly, also still it can be safe. Okay, so let me apply the equation like this. When s equals 250, then the displacement is equal to 252. So this is the minimum acceleration value we are going to find. Let's apply s equals ut plus half ut squared for the car. All right. The displacement of the car, if we take it as 252, right, then initial velocity is 0 plus half into acceleration we have to find, and the time is 10 square. Car has traveled a total time of 10 square, right? 10 square. Then it will be 504 divided by 100. That is a. Therefore, a, I'll put it as a1, right? A1. We're getting A1 5.04 ms minus 2. Okay, so if the acceleration is 5.04, the car will be exactly at 252 meters when the bomb lands on the ground. All right, so the acceleration must be less than that. So safety, acceleration of the car must be less than 5.04 ms minus 2. Okay, right. And the next part, when s is equal to 292 meters, then let's apply the equation. Yeah, right. Let's say car is here when the bomb lands. Then let's find out what is the acceleration. Right. So for s, you have to put 292. Initial velocity is 0. So that part becomes 0 plus half into acceleration we have to find for car into time, 10 square. So that is 100. So it's 2 goes up, it becomes 584 here divided by 100. That is a. Therefore, a here, a2, mark it as a2. The other acceleration we are getting is 5.84 ms minus 2. Okay, so what can I say here? So for safety, acceleration must be greater than this 5.84 ms minus 2. In the question they have asked, what is the range of value of a which will put the car in danger? Therefore, the range is going to be between 5.04 and 5.84. If the car travels at an acceleration of 5.04, when the bomb lands, car will be here. And if it travels with an acceleration of 5.84, the car will be here. So if the acceleration of the car is in between 5.04 and 5.84, it's going to be here, which is the danger zone. All right, so let's conclude. What can we say? So if the car will be in danger of severe damage when, what can we say? Our value for acceleration is greater than 5.04 ms minus 2. If not, yeah, if the acceleration is greater than 5.04 ms minus 2, it should put it here, and less than 5.94, sorry, 5.84 ms minus 2. That is the range. Because if the acceleration is greater than 5.84, car will be here, somewhere here, and the car will pass this point. Therefore, it's safe. If the acceleration is less than 5.04, car will be somewhere here. So there also, it's safe. Hence, this would be the final answer for that question.